All right, we're going to look at proofs of this for this lecture. There are quite a few proofs, so hold on to your hats and put on your thinking caps because there's a lot of stuff going on here. You might want to review this just to check to see what's going on, because sometimes some of this is easy to miss important details. All right, so first we're going to introduce a lemma, which is a small result that's used to prove the bigger results. Lemma 1 says that for any x and x star, in this case, x star is not necessarily a minimizer, just any x star, just a different vector than x. The difference in norms between ax and b and x star minus b is equal to this stuff. Okay, I have the norm of a times x minus x star, quantity squared, and then this inner product thing, this cross term. So let's see how this works. Again, we've seen this actually before. Let's go through it again just to understand it, because this is used quite a bit in the proofs to follow. So the norm of ax minus b is the inner product of ax minus b with itself. I'm going to add and subtract x star to each of these x's. Okay, actually subtract and add. And then I do the matrix or the vector version of FOIL. So here's the four terms: first, inners, outers, lasts. This term here basically is a times x minus x star norm squared. And this term here is a x star minus b quantity squared. These two terms are symmetric with respect to each other, and so we get this condition. I can take them in either order. And now to go from this step to this step, I notice that I can take a to the other side of the inner product by taking the adjoint of it. Okay, I can take a over to the other side of the inner product. So this then is the results. And so I see I have 1, 2, 3, 4 terms here. All these 4 terms are in this expression. So basically, if I take this term over to the other side, I get these 2 terms. And that's the proof. Now, a common form that we will be using of this uses delta, where delta is equal to x minus x star. Or another way of saying it is that x is equal to x star plus delta. X star plus delta. And so then we get the same kind of thing. And instead of having x minus x star here, we have delta and delta. Okay, so this is the result we're going to be seeing this used quite a bit. Next, we have this next lemma. Given some m by n matrix x, suppose that xb is equal to 0 for any b. The lemma says that x itself is equal to 0. Okay, so how do we actually go through and prove something like that? So notice that x itself is an m by n matrix. B is a column, n-dimensional column. So this product is just a single column, and so this itself, xb, is not enough to say that x is 0. That just means that b is in the null space of x. That's all that it's saying. But what this is saying, what this part of the theorem says, is that xb is equal to 0 for any b. Okay, so that's a little bit different. Since it holds for any b, that's important. All right, so the proof goes like this. Since xb is equal to 0 for any b, then let b be any of the columns of the identity matrix. Okay, so this is the ith column of the identity matrix. And so since b is that column, then x times that column is equal to 0, and this is true for any of the columns of the identity matrix. And so this is actually a set of n equations that we can set side by side, x times the first column, x times the second column, all the way down to x times the third column, the nth column, and each of these columns is equal to 0. So that's equal to 0, that's equal to 0, all the way down. Now here I have a matrix, and each of the terms is multiplied on the left by x. I can factor out x out of this expression. And when I do, what's left is the identity. So what this term is saying is that x times the identity is equal to all this, which is zeros. But x times the identity is just x, and therefore x itself is 0. So we have proven this. So this is an example of how you would prove something like this This type of proof will come in handy for you. All right, now for the overdetermined problem, we're first going to look at the point solution. In the point solution, it says the vector x is a solution to the minimization problem if and only if it satisfies the normal equation. The if and only if implies the need for necessary and sufficient conditions. Okay, so for this to be true is sufficient for this to be true. This condition is necessary for that to be true. So there's the necessary and sufficient conditions, and so we'll prove each of those separately, the sufficiency and the necessity. So first we do the sufficiency. That is, we assume that we start off assuming that x star is the point solution, but that the normal equation is not satisfied. Okay, so you can see by the way we're starting off that we're approaching this using a contrapositive argument. Okay, remember, contrapositive argument, we assume the hypothesis and not the conclusion, and then we show there's a contradiction with the hypothesis, that the hypothesis itself must not be true. Okay, well, let's take a look at the proof. So we start with this sufficiency. Suppose that x is a point solution, but the normal equation is not satisfied. So we pick some value alpha, positive, and define delta naught to be this quantity. So notice that all of this is not 0, and so minus alpha times that is not 0. So delta is not 0. And so now we're going to define x as x star plus delta naught. And we've gone through and shown in the corollary that this quantity is equal to this. Okay, it's equal to that. And now I keep track of the fact that this quantity itself is equal to minus delta naught over alpha. And so here we have minus delta naught over alpha. And so that's our quantity. I can take out alpha out of this inner product, and so I get this expression. Okay, so that's what I have. Now, in this case, I'm going to consider two cases. So for the sufficiency, the first case is when a times delta is equal to 0, and then I'm going to come back and look at what happens when a times delta is not equal to 0. Okay, so when a times delta is equal to 0, we have that this difference in norms, I would have a times delta squared here in norm, but that's equal to 0. So that term goes away, and I'm left with this. So what's this? This quantity is positive. This quantity is positive. So all of this is negative. So what that is saying is that this norm is less than, strictly less than this norm. That shows that x plus delta gives a smaller norm than ax star minus b does. So that means this quantity gives a smaller minimum than this, which means that x star is not the minimizer. We contradict the assumption that x star is the minimizer. Okay, so by contrapositive argument, we have shown that in this case, x star is not a minimizer, and so by contrapositive argument, the situation holds, sufficiency holds. So we assumed a delta is equal to 0. What happens if a delta is not 0? In that case, the norm of a delta is not 0, and so we can define this positive quantity alpha. Okay, and so again, the difference in norms is equal to, it simplifies down to this, a delta norm squared, minus that. And so again, that's a negative, and again, it contradicts the assumption that ax star is a minimizer. So regardless of whether a delta is 0 or a delta is not 0, we see that by assuming that the normal condition is not satisfied, we contradict the assumption that x is a minimizer, and so we have proved the sufficiency by contrapositive argument. Okay, so that's the sufficiency. We move on to the necessity. Suppose now that the normal equation holds, that is this. From this, we know that for any x, and let delta equal x minus x star, that we have this, again, we have this set of inequalities from our corollary, or actually the equalities from our corollary. But in this case, this quantity is 0. this quantity. That means this inner product is 0, and so all of this stuff is just equal to this, but so for any x, we see that this is greater than or equal to 0, and so this difference in norms being greater than or equal to 0 establishes the fact that x star is a minimizer. So we have shown the necessity. The necessity in this case was much easier to prove than the sufficiency. So that's the point solution. Let's move on to the solution map. So B is a solution map if and only if A adjoint times AB minus I is equal to 0. So the proof says this. The matrix B is a solution map if and only if any solution X formed from it, X is equal to BB, satisfies the normal equation. So here's X star. Okay. Notice with this expression I can factor out B. And so the only way that this can be equal to 0 for all B, we saw that in Lemma 2. This equaling 0 for all B means that this quantity must be equal to 0 for all B, and so must be equal to 0. So that's the stated condition. So we use that Lemma 2 to prove that this equality must hold. Boom. There's the proof of the overdetermined case. We now move on to the underdetermined case, which says this. The vector x star is a solution to this constrained minimization problem if and only if x star is a solution and x star is in the range of A adjoint. So we got a little stuff going on here. What does that even look like? What's that all about? So again, because we have if and only if, we have to prove both necessity and sufficiency. So we start off with the necessity in this case. So necessity. Suppose that we have a solution, x star is equal to B, and x star is in the range of A adjoint. So what does this mean? X star being in the range of A adjoint means that there is some u such that x star is equal to A adjoint times u. Right? To be in the range of a matrix, that means there's some vector that got you there. Okay? So I don't know what u is, but there must be some u such that x star is equal to A adjoint to it times u. Therefore, the inner product of x star and delta for any delta where x star is A adjoint u times delta is equal to the inner product of u times A delta. Okay? So this is for any delta. So if x is any other solution of this equation, ax is equal to b, then we set delta equal the difference between x star and x. And we have already seen that delta must be in the kernel of A. Whenever you have a difference in solutions, that difference, delta, must be in the kernel of A. Therefore, x star times delta, which is u times A delta, since delta is in the kernel of A, this must be equal to 0. Therefore, x star delta must be equal to 0. And so when I look at the difference in the norm of x star plus delta squared, I can go through and show this equation. So this is a version of that corollary. Okay, and I can show that the difference in norms between these two is equal to delta squared, which is greater than 0. So if x is any other solution, which means x is not equal to x star, which means delta is not 0, that means the norm of delta is positive. Okay, so this shows that x star is a minimizer. Okay, because remember, our problem says we're minimizing x. Okay, and so we have this. So we have proven the necessity. We move on to the sufficiency. Suppose that x star is a minimizer, then we must have ax star equals b, or else the constraint is not satisfied. That's part of the constraint of the constrained optimization. Since x star is a minimizer, then for any delta in the kernel of A, x star plus delta squared minus x squared is, so this is just from that corollary, Okay, I get this. And then, so all of this must be strictly greater than 0. So now what's going on here? What's going on here? So we're going to define two orthogonal subspaces. M is the kernel of A, the null space, and L is its orthogonal complement. Okay, so the direct sum of the orthogonal complement with the space is all of Rn, and the intersection is 0. So we can uniquely decompose x star into two vectors, one that's in the subspace and one that's in its orthogonal complement. Okay, since U and V live in perp spaces, then their inner product is 0. And so x star squared is equal to U plus V squared, and by the lemma in the lecture, we saw that because these are orthogonal, their sum norm squared is equal to the sum of the norms squared. Since U is in the kernel of A, then A times x star is equal to A times U plus A times V, but this is 0, so I get A times V. Since x star is the minimizer, this means that U must be 0. Why? Well, since the norm of x star is 0, and since U does not contribute when I multiply by A, then I can reduce the size of this by making this 0. So U must be 0. So what does that mean? That means x star is just V, but V is in the null space orthogonal complement, the complement of the orthogonal subspace. And so therefore, x star is in the range of A adjoint, because the null space orthogonal complement is the range of A adjoint. Whew! So there's this thing, and I'm going to show that in a little bit, but that is the proof of the sufficiency. Boom. All right. Let's move on to the solution map for the underdetermined case. The matrix B is a solution map if and only if the normal equation is satisfied. So first of all, we have this lemma that says this equation is equivalent to these two conditions. So let's first prove this lemma. So given that this is 0, we have, just multiplying through, that A adjoint is equal to B A adjoint. Okay, so now if we take this quantity and take the adjoint of it, the adjoint of this says that A is equal to A adjoint B adjoint. So that is, if I take the adjoint of a product, I get the adjoints of the individual terms in the opposite order. So the adjoint of A adjoint is A, the adjoint of A is A adjoint, and the adjoint of B is B adjoint. So we get A is equal to this, multiplying by B, multiplying this equation through by B, we get A adjoint, B adjoint. But A adjoint, B adjoint is BA quantity adjoint. So that shows that BA is self-adjoint. Okay, anytime I have a matrix times its own adjoint, that matrix itself is self-adjoint. Okay, so we have shown this this condition: BA is equal to BA adjoint. Okay, so continuing on, we also use again the fact that A is equal to so this equation. I'm going to recall that this is self-adjoint, so it's equal to BA. So I'm sorry, this quantity is equal to this quantity adjoint, but this adjoint is self-adjoint, and so BA quantity adjoint is equal to just BA. So A is equal to ABA. So that proves the second part. Okay. So assuming now that both BA and this hold, conjugating the second equation, so I've shown that if this condition is satisfied, then both of these two conditions are satisfied. So what happens if both of these two conditions are satisfied? Is that equivalent to this condition? Okay, so assuming now that both of those two conditions hold, we conjugate this condition and get this. We use the fact that this, A adjoint, B adjoint, is BA quantity adjoint. That is self-adjoint, so I get this. Okay, I move this term over to the other side and factor out A adjoint, and I get this condition. So I've shown that those two things are equivalent to one another. Cool. All right, now let's go on to prove the solution map. So first we do the necessity. Suppose that this equation is equal to 0. By the lemma, these BA is self-adjoint and A is equal to ABA. So now define X star as B times little b. Since a solution to the linear algebra equation x naught exists, that is, there is some x naught such that ax naught is equal to b. Okay? So remember that for the underdetermined case, at least one solution must exist. So in this case, x naught is one solution that exists. So we can define now a times x star as a times b times little b, but but b is equal to ax naught. Okay, b is equal to ax naught, so I plug that in here. ABA is just equal to a times x naught, but ax naught is b. Therefore, ax star must be equal to b. For b defined this way. So x star then is a solution. Furthermore, x star, given by this expression, is equal to b times little b. Little b is equal to a times x naught. This quantity is self-adjoint, and so its adjoint is a adjoint, b adjoint. So notice that I have a adjoint multiplying by some vector. That means that x star must be in the range of a adjoint, because x star is equal to a adjoint multiplied by some quantity. Therefore, x star is in the range of a adjoint. And so we satisfy both conditions. So we now move on to the sufficiency. Suppose now that B is a solution map. Thus, for any B, x star equals B, capital B, little b, that this satisfies ax star is equal to b, and by theorem 3, x star is in the range of a adjoint. Thus, there exists a u, again, such that x star is equal to a adjoint times u, and again, this x star must be equal to b times b. But b, little b, is equal to a times x star. Okay, and so if I take this over to the other side, 0 is equal to x star minus ba x star. I can factor out x star on the right and get this. But x star is equal to a adjoint times u. And this is equal to 0. This equation must hold for any u, and therefore the matrix itself must be equal to 0. So we have the same kind of thing like we had before. Okay, like we had before. So, boom, proved. Now, what about this null space fact? Is in fact the kernel of A orthogonal complement, is that really the range of A adjoint? Let's find out. So, there are 4 important subspaces for any matrix. The 4 important subspaces are the range of A, the null space of A, the range of A adjoint, and the null space of A adjoint. Okay? So this connects the range of A adjoint with the kernel of A. So let's prove this. in order to prove, so notice that these two are sets. In order to prove that these are sets, that these two sets are equal to each other, I need to show that this set is contained in this set and that this set is contained in that set. That is, every element in here is in here, and every element in this set is in here. Okay, so I actually have to show two things. It's like an if and only if kind of thing. All right, so we first start off saying I have an x in this set. I want to show now that it's in this set. So if x is in this set, then there must be some w such that x is equal to a adjoint w. That's the definition of the range. Well, now let y be any element in the kernel of a. Okay, so what we need to show is that it is orthogonal to this element, x. So let x, so the inner product of x and y is equal to the inner product of a adjoint w times y. I can, by the property of the adjoint, I can move this a over to this other side and get the inner product of w times a y. But y is an element of the kernel of a. Therefore, this quantity is 0 and the inner product is 0. Since x and y are arbitrary, this holds for all elements of those two spaces. Therefore, x is in the kernel of a adjoint. Orthogonal complement. It is orthogonal to every, so it is orthogonal to every element in the kernel of A. Since it's true for any element of the kernel of A, it's true for all elements of the kernel of A. So x is in this space. So we have shown that this space is contained in this space. Okay, we started off with an element here. We showed that it must be in here. Okay, now we're going to go the other way. Suppose that x is in the range of a adjoint perp. That is the orthogonal complement of the space we were just working with. Therefore, for any z, any vector z, a adjoint z with x must be 0. Okay, so that is, so we're kind of doing this in a roundabout way. Okay, and I'll show how we work with this in just a little bit. So a adjoint z with x must be 0. But this, again, by the definition of the adjoint, I can take this over to the other side. So the inner product of z with ax must be 0. So in particular, we're going to choose a particular z. Here we started with any z. I'm going to choose z is equal to ax, which says this. The inner product of ax with itself is equal to 0. But the inner product of ax with itself is the norm of ax squared. The only way the norm of a vector can be 0 is if the vector itself is 0. That means ax must be 0. This implies that ax must be in the kernel of A. Okay, so what we've said is x is in this subspace, and that implies that x is in the kernel of A, which means this subspace is contained in this subspace. Okay, so we have this condition. So what? So what does this mean? So if you think in terms of Venn diagrams, okay, this set is inside of this set, right? Now what happens if you take the complement? The complement is everything outside of the set. So if this set is inside this set, the complements of the two sets, so if you turn everything inside out, show that the complement of, so this is the smaller set is contained in this set, which means when you take the complements, the complement of the smaller set is larger than the complement of the larger set, and so the containment goes the other way. Okay, and so we have this. The kernel of A complement is contained in the range of A adjoint. So I took the complements of both sides. And that proves the null space fact. There are 3 other null space facts that can be proved. I challenge you to do that. Well, these are our practice problems. These are the proofs, rather. We'll move on now to our practice problems to see how to do some of this stuff.